Hi guys, welcome back to my channel. In today's video, I'll be discussing about the antenna parameters and radiation. So guys, if you haven't seen this playlist radiating systems, I recommend you to see these both videos before this video. The link for this playlist is given in the description. So before I start, I would like to define what is antenna. An antenna is a physical structure which is used as a transmitter and receiver to transmit wirelessly via electromagnetic radiation. So in transmission, an antenna transforms basically a one-dimensional guided wave into a three-dimensional space wave. In reception, it performs the reverse operation. So there are five important parameters of an antenna: gain, efficiency, bandwidth, beam width, and size. Let's discuss this one by one. Before that, I'd like to define an important term called radiation pattern. So the radiation pattern describes how the radiated power of an antenna is distributed as a function of direction. That is, it basically says the electromagnetic fields at a distance r and as a function of theta. So here it's more dependent on the angle. That is, to remove the distance dependencies, we define the radiation quantities in angular terms rather than the spatial terms. So this is the radiation pattern of a loop antenna. This is the radiation pattern and this is the azimuth and elevation cuts. These cuts and the simulation for the radiation pattern I will be doing in my coming videos. So these pictures just I kept for some reference, like how it looks like to get a basic idea. And this is the radiation pattern of a helical antenna. And this is the radiation pattern of a waveguide antenna. Now coming to radiation intensity. So we define radiation intensity as the power radiated per unit solid angle. As you can see, the radiation intensity is a function of only theta and phi. It's defined as the r square into the power density. Even the power density is the function of theta and phi only. So it has the unit of watts per steradian and it depends only on direction, not on the distance. Let us see the radiation intensity of a standard example, which is the Hertzian dipole. So an Hertzian dipole is the electrically very short dipole. So from my last video, this is the far field solution of the electric field component, and the power density is given by this formula. So when we substitute this in this formula and calculate W and then multiply by R squared and you find the radiation intensity, we arrive at this result. As you can see from the equation number 4, we can understand the maximum radiation is at angle 90 degrees and the minimum radiation 0 is along the dipole axis, which is 0 and 180 degrees. The total radiated power. It is defined as the integration of the radiation intensity over the entire sphere. That is basically you integrate the radiation intensity over the entire sphere. This sin theta is the Jacobian, which you will get when you do the axis conversion from Cartesian to the spherical. Now, let us define another important quantity called beam area. Beam area is basically the angular spread of the radiation. That is, you integrate the normalized radiation intensity with respect to the solid angle. For antennas with narrow main lobes, the beam solid angle can be approximated as theta hp multiplied by phi hp, where theta hp and phi hp are the half power the beam widths in orthogonal planes. So this is the visualization of the beam area. As you can see, the beam area is the solid angle through which all the power radiated would pass if the power maintains its maximum value over there and is zero elsewhere. Next is the directivity. So directivity means at a distance r from the given antenna, it is the ratio of the electromagnetic field or the radiation at that point divided by the radiation of an isotropic antenna at the same distance r. It basically measures the concentration of the radiation with respect to a standard isotropic radiator. So for an isotropic antenna, it radiates uniformly in all directions. So the radiation intensity is given by radiation power divided by 4 pi. So now, as I said the definition of directivity above, the directivity is defined as the maximum radiated power divided, sorry, the maximum radiation intensity divided by the radiation intensity of the isotropic antenna. So, which is U max by UISO. If you substitute this in this, you'll get 4 pi U max by radiated power. Now, the radiated power you can write as the maximum radiation intensity multiplied by the beam angle. It's multiplied by the beam area, because the radiation intensity is nothing but the power per unit solid angle. So you just multiply with the beam area, you get the radiated power. Now you just substitute this in the equation number 9. You get the formula for the directivity, which is given by directivity is 4 pi by beam area. This shows that the directivity is inversely proportional to the beam area. Now, this directivity is not directly seen in the practical performances. So, in practical performance, we see the gain. So, gain accounts for the losses also made by the antenna. So, gain is the directivity multiplied with a quotient which is called a total antenna efficiency. It's just the scale version of directivity. The antenna efficiency or the total antenna efficiency is expressed as the product of radiation efficiency multiplied by the mismatch efficiency and the polarization efficiency. Let us see these terms one by one. So radiation efficiency is nothing but the efficiency which accounts for the loss in the radiation. So it is given by the radiated power divided by radiated power plus lost power. Mismatch efficiency. Let's say if we did not do impedance matching, then the antenna input impedance and the transmission line impedance is not matched. So some reflection occurs, and that reflection, we know the formula for the reflection coefficient, which is given by Zin minus Z0 by Zin plus Z0. So because of this reflection, some only a part of power will be delivered to the antenna. Some power gets reflected back. So the fraction of power which is delivered to the antenna is given by the efficiency is basically given by the 1 minus gamma square, where gamma is the reflection coefficient. Now the polarization efficiency. Let's say for a received antenna, you have a polarization filter at some angle. Well, let's say it is at the y-axis. Now, if your incident electromagnetic wave is at angle theta, only the cos component gets uh, absorbed or gets received by the antenna, and you basically neglect the other horizontal or perpendicular component. So if there is some polarization mismatch angle between the incident wave and antenna, let us name that angle to be phi, then the polarization efficiency is given by the cos square phi. Antenna aperture and gain relation. So the effective aperture is defined as the radiated power. It's not the radiated power, sorry. The effective aperture is defined as the received power by the actual power at the point. So to find the theoretical power, you basically from the radiation intensity at a distance r and at a particular angle, you know how much power is there. So just divide the received power by that power. You can understand the basically the loss due to the aperture of your antenna. So using the plane wave power density and reciprocity theorems, the gain aperture relationship is derived as follows. This is the formula. Gain is 4 pi into aperture area by lambda square, where lambda is the wavelength. So another very important formula is Friis transmission formula. So the power density at a distance r of a transmitting antenna is given by, so the power at the distance r is nothing but the transmitted power multiplied by the transmission gain. So this gives the power in that direction, and you just divide by the 4 pi r square to get the power density, because we just assume it's a square at a distance r. Now the power received by an antenna of effective aperture AE. So this is the power at that point. But when you keep a receiving antenna which has effective aperture AE, so it just receives the power W scaled by the aperture area. So this is the received power. Now you substitute the formula for the aperture area in this. So which gives the received power is the transmitted power multiplied by the transmission gain multiplied by the received gain, and this is some scaling factor. So this scaling factor is path loss. So ideally the received power should be only this value, but there is some other value which is coming scaling factor, which is known as the path loss. Note that this Friis transmission formula is valid only under far field conditions, and there is impedance matching and polarization matching. We define this term to be the path loss, which is given by 4 pi r by lambda whole square. As you can see from this formula that the higher frequencies suffer greater free space path loss. So in my next videos, I will be showing simulation of this antenna, guys. Thank you so much for watching this video.